Okay, so hey everyone, my name is Cody Melton. I'll be talking today about correlation consistent pseudopotentials and their use in QMCPACK. So this should be a relatively straightforward, simple introduction, but if anybody has any questions, feel free to jump in at any time. Okay, so in order to do an accurate quantum Monte Carlo calculation, anybody who's done them before knows that you need to use pseudopotentials. And the accuracy of quantum Monte Carlo doesn't actually get you anywhere unless you're solving for the correct Hamiltonian. And so that's the purpose of this talk is in order to actually solve and directly describe the electronic structure of correlated materials accurately, we need good Hamiltonians. And these are coming from the effective core potentials that replace the core electrons in the system. So using effective core potentials are nice because they allow you to tackle larger and larger systems, but you can also include things like relativity, etc. So we sought out to construct a new generation of pseudopotentials to replace some of the older pseudopotentials that have been used in quantum Monte Carlo calculations that are highly accurate and isospectral to the original many-body all-electron Hamiltonian. So the way in which we do this is to use a many-body construction. Namely, we construct our effective core potentials from many-body spectra, which is intended to lead to the reproduction of almost exact many-body properties, from band gaps to cohesive energies to binding energies of molecules, etc. We also want our ECPs to be reliable and universal, namely a simple form that can be used in many different types of codes, both at the mean field and the correlated level. So the ECPs that we use are relatively straightforward in terms of their parameterization. So if we have the valence Hamiltonian here, we can write down the pseudopotential in this form, which is semi-local. So the pseudopotentials use a semi-local projector. So namely, we have projectors over the spherical harmonics. And then the radial dependence is fully local, which is just expanded in some set of Gaussians. So we have expansion coefficients, Gaussians, and then some radial prefactor. So this defines the set of parameters that actually go into our pseudopotential, and that's all we have to do. And then to actually optimize these, which is where the many-body information comes in, we use an objective function that includes both many-body energy consistency and norm conservation. So the real deviation from previous pseudopotential constructions comes in this step. Most pseudopotentials have been generated from, say, Hartree-Fock or density functional theory, but we instead use couple clusters, singles, doubles, perturbative triples, and match our ECPs to have the same energy gaps as the all-electron relativistic couple cluster. And it should be noted that whenever you're doing couple cluster on atoms, it actually agrees to the experimental atomic energies to less than 0.03 eV. So if our ECPs actually reproduce these energies, then we actually agree to experiment. And then in addition to add in a little bit more transferability, which I'll talk about later, we also include norm conservation into our objective function when optimizing these pseudopotentials. So this just involves the norm inside of a particular cutoff radius, the value of an orbital at a given cutoff radius, derivatives, and eigenvalues. And so we just optimize and minimize this objective function with those parameters to generate our pseudopotentials. To just kind of give a motivation on kind of describe the quality of these pseudopotentials. This is just a simple example looking at the oxygen atom. So what I'm showing on the left is the atomic spectrum from oxygen. So in the first column, we have the ionization potential. In the second column, we have the electron affinity. And in the third column, we have a mean absolute deviation for a wide variety of atomic states. And this is the deviation from the all-electron couple cluster compared to different types of pseudopotentials. So above this horizontal line are different types of pseudopotentials that have been used in the past. So if you're familiar, Burkowski-Philippi-Dolg pseudopotentials, and then a variety of superpotentials coming from the trail and needs group. You can see the discrepancies from the all-electron. Then also on the top, this UC is what we call an uncorrelated core. So this is an all-electron calculation at the coupled cluster level, except that we do not allow for correlations coming from the core electrons. So in oxygen, when you pseudoize oxygen, you remove the 1s level. An uncorrelated core actually doesn't allow correlations from that 1s level. So you're only allowing for valence-valence correlation, and you don't allow for core-core and core-valence correlations. But it's an all-electron calculation. So as you can see, if you focus on this spectral ECP, which is actually using an objective function that completely neglects this norm conservation, you can see that compared to all other core approximations, our constructed ECP does significantly better on both ionization potential, electron affinity, but also the mean absolute deviation over all of the states that we considered. And on the right, unfortunately, it's not showing up color-wise, but I guess I'll still explain it. So what I'm showing here is a oxygen dimer, and it's the discrepancy from the all-electron coupled cluster binding curve. So this vertical line is the all-electron equilibrium bond length, and on the short bond length side, we're calling this the dissociation threshold. So this is where binding energy of a molecule goes towards zero, which if you were to then translate this into solid state, for example, this would correspond to high pressures. So as you can see, there's quite a bit of scatter in terms of the discrepancy, especially as you begin to compress these bonds. I think it's a little hard to see, but I think this is a trail needs pseudopotential. You can see as you begin to compress the bond, the deviation from the all-electron gets significantly worse. Whereas the spectral ECP that I highlighted over here has relatively flat air throughout the entire binding region and relatively small air, especially near equilibrium. And what this indicates is that if you have small air throughout the entire binding region, you have accurate vibrational frequencies. Small deviation means that your binding energy is good, etc. So it's hard to, it's not showing up so well on the screen, but
let's try something here.
Okay. It's a little bit better.
A little bit bigger on the projection, but it's still a low resolution in the PDF, I think.
Yeah. Yeah.
It's fine on this one. It's strange.
Can you actually see the? Yeah, you can actually see the colors on this one too. A little bit better. Anyway. All right. Anyway, so the point of this slide is to just indicate that by comparing to a bunch of different molecules that we did with our ECPs, and comparing the dissociation energy, the equilibrium bond length, vibrational frequency, and the air at the dissociation threshold, so this compressed bond length region, our ECPs do significantly better compared to all of the other core approximations that you could potentially choose, particularly to use in your QMC calculations. Everything I just showed was just for first row elements, but we also have transition metals, which I know that everybody, or a lot of people are going to be interested in. So just to briefly go over this, basically we have the same kind of calculations before, relativistic, all-electron coupled cluster is our reference. We have the uncorrelated core, which is an all-electron coupled cluster, and then a number of different pseudopotentials that we're testing against BFD, some Stuttgart ECPs, a correlated version of trail needs pseudopotentials, and then our pseudopotentials. And this is all the transition metals, and this is also a discrepancy for a particular atomic excitation. So this is an S to D transition in the neutral transition metal, ground state, ground state to the S going to a D. And as you can see, these diamonds are our correlation consistent ECPs, and the air is relatively flat and actually quite small compared to a very large scatter for a lot of these other core potentials. If you ionize all the way down to the argon core, you can see that the air grows significantly for all of the other core approximations as opposed to ours. Ours stays relatively flat and grows slightly as you increase towards zinc, but the relative error is still quite small. And lastly, I'm showing a mean absolute deviation over a wide variety of states, which is shown here on the left, an example spectrum for nickel. And as you can see, again, the errors compared to all of the other transition metals, or sorry, all of the other core approximations is quite small, and actually smaller than the uncorrelated core for all of the transition metals. So all this to say that our ECPs, we believe, are quite accurate and useful, and we hope that you start to use them. And so we hope that we make it easy. We were hoping to make. Okay. Well, in that case, I'll go back. Just one last, just kind of showing how accurate the ECPs are. This is a similar binding energy plot compared to the as I did for oxygen, but now this is transition metal oxides, so scandium oxide and vanadium oxide. These dark lines here are showing the discrepancy, and as you can see again, our discrepancies are relatively small and flat compared to a lot of the other pseudopotentials. In particular, if you look at VFD, for example, especially if you begin to compress the bond, you can be making significantly large errors compared to the all-electron Hamiltonian that you actually care about calculating. So we hope that we're making these pseudopotentials easy to use, and so we have decided to put them on a website so that everybody can download them and use them. And so the website is pseudopotentiallibrary.org. So if everybody has, connected to the Wi-Fi, you can actually navigate here and click around and find your favorite element. So whenever you navigate there, you should find a periodic table that looks something like this. All of the dark elements are ones that have a pseudopotential that you can use. So notice there's a few missing over here, and then everything as you get heavier is missing. But it should be noted that this is constantly being updated as new ECPs become available. So, and actually very soon we'll have completed up through Krypton. So everything up to here will have an ECP available for download and use. And if you have any pseudopotentials that you have developed yourself that are you believe are accurate and you want people to start using, or be tested against our pseudopotentials, feel free to contribute them to the GitHub page. You can just do a pull request. Okay, but just to kind of describe what all the information that's there, if you go to the pseudopotential library and, for example, click on carbon, you'll see a number of different little tiles pop up. And it's hard to see here because of the projector, but this first column, or this first one will be CCECP. So these CCECP represents the correlation consistent pseudopotential that I'm talking about. And then there are other ECPs that you can also test against. So the two that are actually included here are from the Trail Needs group, so titled ECEPP and CEPP, I believe. But these are another set of correlated pseudopotentials that you can download for carbon. But I'm focusing on our correlation consistent pseudopotentials. So if you navigate to this page, you can click on the c.ccecp file, and what you should see is this pop up. It's just a little text, just a text file that has the Gaussian parameterization of our pseudopotential. So if you're interested in running a code that we don't have a converted file for, like a quantum chemistry package, say MolPro, or I don't know, some other quantum chemistry package that uses a particular format, you can just convert this into their format. So just to briefly describe what that is, for carbon, when you pseudize, you have 4 electrons. So the first number is the number of electrons. And then the second number is telling you how many channels are in the potential. So this is telling us that we have 2 channels, which means that there's an S channel and a P channel. And then in the S channel, there's one set of Gaussian expansions, and then the 3 parameters for that. And then the second channel, which is for the P channel, has 3. And so there's a sum of 3 different Gaussians that have those individual parameters, which are described up there. Okay. So that format that I showed may be slightly confusing. So if we've actually provided a number of existing formats for different quantum chemistry software that actually directly interface to QMCPACK. So all of the codes that you would be using directly with QMCPACK that already have converters for, we have the files for. And with each CC-ECP, we include a basis set. So if you're familiar with the Dunning basis sets, we have correlation consistent with polarization, V and Z, so double zeta, triple zeta, quadruple zeta, and quintuple zeta basis sets. And for some, we also have augmented versions. And so for each of these basis sets and ECP formats on that website, for each code that QMCPACK interfaces to, we have a file that is just appended with the .games or .nwchem, which is the file format that you would use for your given code. So even though games, I don't believe, is being covered at this workshop, if you were to use the games code, you would just download the .games files. But I believe Anwar will be talking about Quantum Package later, and I believe that Quantum Package uses the games format, so you can simply just download the .games formats to use directly within Quantum Package as well. And also, ISCF is a code that was just fairly recently been interfaced to QMCPACK, and it actually parses the NWChem software format. So we actually have provided NWChem formatted files so that you don't actually have to go through and do the conversion yourself. And then lastly, to actually run in QMCPACK, you just need to download the .xml file. So this is the way that QMCPACK will read it. But these you'll just download to use within your particular software. So now I want to move to the Okay, right. So just to go through a brief example, which will just have the input files, just to kind of show a way in which you can download these. If you go to the GitHub page and go to day1_CCECP and then files and then quantum chemistry, you'll see, so I'll actually go back one so that you can see it. So QMCPACK workshop, day1_CCECP and then files. So this is kind of a straightforward example on how you would just interface and use our ECPs with PySCF. So if you don't like navigating to a website and downloading the files directly, you can just use a wget. So for example, you were going to do a wget and run a games calculation on, say, water, you would need to grab, a triple zeta basis on games, the ECP, oxygen, and the ECP file. But since this example, which you can go through later, actually uses PySCF, since it's Python, it's actually quite nice. You can just go ahead and directly download the files within the input file that you're running your PySCF in the first place. So I actually just created a little template that you can modify for whatever application that you're doing, and it will just go ahead and grab both the basis set that you specify. So I'm specifying a triple zeta, specifying I want the CC-ECP instead of another ECP, and then it will just grab the basis set, the ECP, and we'll also grab the XML file for QMCPACK calculations later, and then grab them. And then in PySCF, you can simply just open the files for the basis file, open the file for the ECP, and then just directly parse those. And so it's as simple as that. You simply download the file, and then you can open them. And it should just automatically work. And so now I have a Hartree-Fock and a PBE calculation that you can run, and assuming everything goes well, you should see those energies. But PySCF, which I know will be covered later, also can run solids. And using Gaussian basis sets and solids and with our ECPs is actually just as straightforward. All you have to do is download the files. There's only one caveat if you're doing solid state calculations, in that when you're doing Gaussian basis sets in periodic boundary conditions, Gaussian basis or exponents in the Gaussian basis set that are too diffuse, namely small exponents, can cause linear dependence issues, and make it difficult for the SCF to actually solve. And so if you want to use our ECPs within PySCF, the only thing that you have to do, so I'm not going to go through the example in detail, but all you have to do is whenever you download the file, so here I downloaded a double zeta basis set, downloaded the ECP, read it. The only thing that you need to do is add this cell.drop exponent. So I chose a threshold of 0.1, so this will drop all exponents in the basis that are below 0.1, and this should facilitate convergence at the SCF level.
Well, a question, I mean, how accurate is that compared to doing plane waves? I mean, is this good enough for carbon diamond, or should people set extra carefully and maybe explore their own?
So I'll actually show that in a second. So actually, if you run through this example, just downloading the double zeta, just to give an idea, if people are familiar with plane waves, knowing what kind of accuracy you're going for a plane wave convergence. If you just run the double zeta, you should see an energy that is negative 10.2576 part rate. So you may not know what the energy is supposed to be, and you may not know that double zeta is enough. So if we actually run through and increase the basis to a triple zeta and rerun the same calculation, you'll see that you get roughly an 18 millihartz increase in the energy. So then the question is, are we actually converged or not? So if you actually then try the quadruple zeta, I didn't test it on the Amazon Web Services, but you'll notice that there's singularity detected in overlap matrix, and overall accuracy may not be enough. You can adjust blah, blah, blah. So this is indicating that as your basis gets too large, sometimes the SCF in periodic boundary conditions can be somewhat problematic. And this will be an indication that you need to either modify your basis in some way. And if you need to do that, I did not have time to go through all of the details here. Let me actually zoom down a little bit. But I provided a number of links here that you can give you some advice on how you would actually go about modifying a Gaussian basis set for a solid state calculation. But in general, if you're using a specific pseudopotential like ours or BFD or whatever, but in your Gaussian basis, whatever the contracted basis functions are, they have to be specific to the ECP that you're using. So one of the ways that you can do that is just optimize an individual atom, do a calculation to generate your contractions. And all of that information is actually going to be in these two links at the bottom, where people will go through and show you how to modify Gaussian basis sets. And then also, whenever you have primitives in your Gaussian basis set, for the most part, those are relatively transferable from other calculations. So I've actually provided links to crystal basis sets that have been used and published in calculations before, where you can actually just grab the primitives from there. And again, all of that information will be described in these links if you are interested or have trouble, assuming that you download our basis sets and they don't work. But let's just try to remember this number, that negative 10.275, for a few minutes. So this was a triple zeta basis, and I'll come back to that in a second and compare it actually to a plane wave calculation. Where is the talk? Go back to the talk. Okay. Okay. So that. Okay. So lastly, I want to talk about our Gaussian basis sets, using our ECPs with Gaussian basis set codes. So how do you, if you want to do plane wave calculations in Quantum Espresso, how would you go about using them? So the main thing is that you need to know that if you're going to use a plane wave code like Quantum Espresso, they actually use a different formulation of the pseudopotential. So the semi-local potential is what we parameterized, but the plane wave code uses a different form known as a Kleinman-Bylander projector. And doing this transformation is not exact, and it can cause issues known as ghost states, which are low energy states that have the wrong number of nodes. And whenever you actually carry this over into the quantum Monte Carlo calculations, this can cause unphysical energies, and you can have difficulty optimizing your wave functions, large variances, the Walker population in diffusion Monte Carlo can become unstable, etc. And if you want to see more information about how severe this can be, there's a paper by Drummond, Trail, and Eads talking about this. But in addition to ghost states, because this transformation is not exact, it's only exact for a particular atomic state. And then if you're trying to use the potential in a different atomic configuration or a molecule or whatever, they may not behave the same. And so there's issues that come up with transferability, namely the ability of this Klein Violander potential to behave like the semi-local potential. And so these are things that you need to keep in the back of your mind. But recently, some of the work I've been doing is modifying a version of the OPM Code, which is a pseudopotential generation tool. And I've modified OPM to be able to take in our semi-local pseudopotentials and do plane wave or do testing for transferability, do testing for ghost states, also give information about suggested plane wave cutoffs, etc., so that hopefully people can just download the files and use them. So again, it's kind of hard to see, but if you go back to the pseudopotential library and actually click on carbon again, you'll see at the bottom there's a C.RPT and a C.UPF. So if you want to use Quantum Espresso, the C.UPF is the pseudopotential file that you would need to use in Quantum Espresso. But there's relevant information added in this C.RPT, which is coming from the OPM code that I've modified to do this. And it will provide information about ghost states. So you can see there's a bunch of no's here, which indicates there's no ghosts. So that at least for this carbon potential, there should be no ghost states. So you should be able to use it without those kind of variance problems or diffusion Monte Carlo problems, problem optimizing, etc. Additionally, in the report file, there's information about the suggested cutoff. So if you're interested in, say, 1 milli-electron volt convergence error per electron, you notice here there's a cutoff of 162 and a 238. So what you would do in your Quantum Espresso input, you would just grab the 238 since that's the larger of the numbers, and then this would be the cutoff that you, or the plane wave cutoff that you would use in your plane wave code. And so this .report file gives you suggestions for actually how to use our potentials without you having to go through and do all the testing. And I'll show you that that actually works in a second. But it also has information about the transferability. So this is actually testing the semi-local evaluation, which is the normal potential, compared directly to the non-local Klein Violander version of the potential for a number of different atomic states. And you can see that the relative error is quite small. And so this is indicating that this UPF file should be reliable for use in different systems compared to the semi-local potential that we actually generated. Okay, and then lastly, I need to go back one more time. Okay, sweet. So I have an example worked out in here as well that you can run through later. But again, you can just download the UPF and the .report file, and this has kind of describing the same stuff I just talked about, ghost states, the transferability issues, the suggested plane wave cutoff. So recall that with the Gaussian basis set and the triple zeta, in PyCF, whenever I ran diamond, this was the diamond primitive cell at the gamma point, I saw that there was an energy of negative 10 point, what was it? Negative 10.275. And if I look at this .report file, I'll get a suggested cutoff for carbon, and it says that it's 238. So here's an example input to Quantum Espresso, and I actually just use the 238, and then the cutoff on the density we typically take is 4 times the wave function cutoff. And then the only other thing that you add in there is the UPF file, which is our ECP, just the Klein Violander version of it. You run this diamond calculation, and you actually grab for the energy, and you'll see that it's negative 10.2777. So it's roughly 2 millihartz lower than the triple zeta basis that I got out of PyCF. And if I actually then do a scan around that, you can see that by the 238 that was suggested in the .report file, I'm basically converged to 0.1 millihartz already. So this is already suggesting that the 238 Rydberg that's in the .report file should be reliable as a plane wave cutoff, and also a triple zeta in the PySCF is actually almost fully converged. So that's just kind of a simple example that you can run through later, describing how you would actually use these. And one final comment is that if you actually begin clicking around on the pseudopotential library, you'll see that the .upf files only exist now for hydrogen, boron, carbon, nitrogen, and oxygen, I believe. And these are being updated as I test those files. So very soon, we should have more UPF files up through the second row, and then soon to the transition metals. But in the interim, if you need to do, say, a transition metal calculation, there's actually already a set of pseudopotentials that have .upf files that were developed by Jeremy Krogel, published in 2016, that have the tags RRKJ and TM that you can just download and use in your application as well. I think that's about all that I have.
Summary slide?
Oh, I think, yeah, I do. It's basically everything I've already said. But yeah, just to summarize, if you're doing a quantum chemistry calculation, just grab the files that are .nwchem or .games, and that should allow you to interface directly to games, PySCF, or quantum package, and more details about using those codes will be discussed later in these tutorials. And as I said, the number of UPF files is limited, but there's already a good set there that you can use in the interim, the RRKJ and TM. And then the only thing you need to remember is to download the .xml, and then you can use it directly in QMCPACK. So, I think that's it. If there's any questions.
Questions for Cody?
For the at least running molecular with the Gaussian basis sets, do you have to did you have to re-optimize or at least recontract?
When developing the basis sets?
Yeah, from
Yeah,
the
so any contraction needs to be tailored to the specific ECP. So
yeah.
we actually designed these from we took a basis set that was for another ECP and actually just recontracted them basically.
Okay.
So that's how we have the triple zeta, quadruple zeta.
Okay, so those are the ones
They're already
available or
recontracted directly
recontracted.
for the pseudopotential that you'll be downloading. So you should just be able to download and directly use them. If you have a more difficult problem where you need to uncontract, you can do that, and that is general.
Yeah, I didn't understand what you were saying about uncorrelated core and what was the point.
Yeah. So the question was, he didn't understand the point of me talking about the uncorrelated core or what that was. So let me go back. I'll just go here. That's fine. Doesn't really matter. So the uncorrelated core is an all-electron couple cluster calculation. The only difference is that you can decide where you do all of your excitations from, right? Your single excitations and your double excitations. And you can cut off where you allow those from. So whenever I talk about my all-electron reference, which in this plot I'm using the mean absolute deviation from that all-electron reference, that is allowing explicit correlations coming from every single level of the atom. So, if I'm pseudizing, let's say oxygen, I remove the 1s. In the uncorrelated core, I'm not allowing any single or double excitations that involve that 1s orbital.
That's why.
Because it still has valence-valence correlations. And it's still an all-electron calculation, and quantum chemists actually use it quite often, where they don't allow correlations from the core because they don't think that it's important.
Put it in a different way. The ECPs include core, and core valence correlation.
Yeah.
While
Because we're
very
matching.
often what you do is uncorrelated core calculation, just frozen core. So what we say is actually that if you use those ECPs, you will be more accurate fundamentally than actually if you use all electron but do not correlate core. Understand?
Yeah, okay, I just didn't see what the point was of not including.
Because if you put 2 or 3 transition metal atoms into the whole thing, you will not correlate the core. I can guarantee you there is no correlation.
The code won't converge, but you can use the pseudopotentials.
It's impossible.
And so our pseudopotentials would have included some of that effect already that you're neglecting by doing the all-electron calculation, but not correlating the core. Any other questions?
All right, so
Oh, yeah.
You have shown that your pseudopotentials are more accurate. And I spoke a little bit about the cost in energy cutoff, how hard they are. Can you say a little bit more how sensitive they are to the basis set as compared to the other Gaussian pseudopotentials?
To the other Gaussian pseudopotentials like BFD or something,
Yeah, so
I would say very similar.
very
In terms of BFD, we're similar in hardness to them, I would say. So you're going to have larger cutoffs. But, compared to the pseudopotentials that, Jaron had, which are 300 Rydberg, we're on that order. So,
Fernando, there is no fundamental difference.
yeah, it's going to be on the order of
You just need to have the right construction adapted to the particular thing. Apart from there, there's no difference with BFD or Stuttgart is even worse.
Yeah, they're extremely hard.
Yeah, so I didn't hear you talking about an archive. If you're trying to do ultra-high pressure calculations. So
right.
sometimes you need very small core.
Ours has the smallest cores of all.
Okay, are those tabulated, the archive somewhere?
I think in the paper they're
It's
put,
in the paper.
and if I can add them to the outputs for the EPS files.
In fact,
I don't know that they're already there.
good
but I
that
can
you
do that.
asked. Cody didn't have time to explain. Cody didn't have time to explain. What we tested was also squeezing the molecule up to the point of dissociation, but on the other side of the curve. They are accurate actually up to that point, which would correspond to 100 of GPA, and so on.
Yeah, but what about many thousand?
Well, you can take a smaller core, and then you should be okay.
So that's actually something you say that a lot of these actually have different valences available.
For the second row,
That's
for
true.
example, we have helium core also. You can use, say, silicon with the helium core, which is incredibly accurate. So you can squeeze it as much as you want.
And the same options will be available on later ones. But the first row, there's only one option, right? So, but the second row has the healing core as well.
just one comment. So I didn't see the site references in your talk, but you have published a series of, I think it's 3 papers now, 3 or 4 on these.
Oh,
and
if you actually go to the pseudopotential library, well,
it's got the reference.
where
So
is
the
it?
pseudopotential library website has got links to the papers.
It's completely invisible here, but under the title of each one is the published paper that is associated with the potential. So you can go to navigate there and read all the information about how they were generated and everything.
Right. So I've actually got 2 questions. I think we have a couple of minutes. So how do you showed the properties for dimers, for example? So
Yes.
sort of a ground state property. How do the accuracies of excitations, compare with what's been done before?
So in the, if you actually look at the atomic states that we use to optimize the pseudopotentials, we have tons of excited states in the atom, both for the neutral, but also various ionized and, adding electrons and anions. So all of the excited states that we can possibly fit into the optimization were used, at least at the atomic level. And from what we can tell, it's carrying over, at least in the ground state properties. I don't know of an application where people have done actually excited state properties using our potentials yet, but I would believe that it would carry over and be quite accurate as well, because we've already filled that in.
Yeah, just a quick, which Cody and Chandler found. There was an independent testing, completely independent of us. There was a Chinese group which calculated a bunch of molecules with BFDs and others, and they explicitly said, the new ones are more accurate. So anyway, that's a good advertisement, I guess.
Okay. So then the second, you mentioned, working on this special version of OPM, and also doing ghost state, some of the ghost states testing. Of course, that's quite new.
Yeah.
So are you planning on making this modified version of OPM available? And then on the ghost state side, do the DFT-based ghost tests that OPM does seem to be a reliable guide to whether you're going to be in trouble in the QMC calculation? Or have you found some cases where maybe the DFT test passed, but then you see the world of trouble when you do a diffusion Monte Carlo calculation?
So I do plan to make the OPM modifications available so anybody can, it's not just tailored specifically to RC ECPs. You can put in any Gaussian parameterized pseudopotential in and create your own projectors and do all the ghost state testing and plane wave cutoff and all of that. With regards to whether or not the DFT ghost state checks are sufficient for QMC calculations, I think is an open research question. But if you look at the Trail Needs paper from 2016, I have it linked in there. There are, for the majority of the periodic table where they had tested potentials, it looks like the ghosts, that if there's a ghost in the DFT, there's a ghost in the QMC, and there's very few examples where the reverse is true, where there's not a ghost in the DFT. I think there are some, so I don't know that DFT is a pure check, so caveat, you should always check your potentials that you're using with the Climate Biolanders on the website just to make sure that your calculations are fully clean. But I think that's an open question. And I've not done any testing myself so far in that regard.
Well, it doesn't make sense to put ghost states in QMC. It's just, you're using the same semi-local form. It's basically, if you get a ghost state in DFT orbital, means you have a wrong wave function. That's it.
Fair enough.
All right, thanks very much.
All right.